We continue on basically with discussion of dark sectors, and today our focus will be on dark matter, and I will provide focus of the whole school is on dark matter, but I will focus my lectures more on dark matter and provide some comments on weakly interacting massive particles, super weakly interactive massive particles, and if time permits, also on bosonic condensate dark matter. So just to recap from what we know from cosmology, the universe was relatively simple early on, fairly uniform and homogeneous, with the small perturbations superimposed on otherwise smooth background, and we see ample evidence for that from the time of the CMB that corresponds to these temperatures roughly. And the dark matter was already in place back then. So at the time of the matter radiation equality, and the CMB shows very clearly that signals from baryons already falling into the potential wells developed by the dark matter. So the dark matter was therefore in place at the time of matter radiation equality. So whenever we think about the history of dark matter, we should go, a little earlier than that, because this is it's clear that this is an issue of the early universe. Moreover, we know that dark matter is not made of ordinary atoms, and there is six times more of ordinary. It's six times more of dark matter than hydrogen and helium. And so, what is it? And as we probably already mentioned, this is not the thermal neutrinos. You can't make them dark matter, because you would have to violate their mass bounds, and moreover, you will not be able to hold it still in a very large, in a very small galaxy-like structures. So they will free stream and they raise this small structure. So they're not a good candidate, but could be a subdominant candidate for dark matter, and it is actually. But then on the other hand, the simplicity of the early universe makes many of us suspect that dark matter may be in some form of the unknown particles. And then we started last time. We discussed a little bit of what can what kind of main mechanisms for generating the abundance of dark matter, and you can really point out several classes such as WIMPs with normal type couplings, super WIMPs, or sometimes called Friesen dark matter, with super small couplings, and the bosonic condensate dark matter that may be not coupled to the Stern model at all. So this is the super cold dark matter, or I do not know a better name. Sometimes it's called displaced out of equilibrium dark matter, which is also not a very good name. And of course, there is a variety of options that I wouldn't touch, but they're of course there to have look at, and this includes primordial black holes and I would say many other macroscopic objects, right? Because um, as I said last time, we have evidence for dark matter at the sort of 10 to the 20 kind of centimeters scales, and then we scale it down to to a lab size and say these are particles. Well, you can achieve sort of a fraction of solar mass per kiloparsec densities, not through this smooth distribution of small particles, but actually by putting big but rare objects as well. So this is an important discussion going on in the literature right now about whether or not black holes can, what kind of fraction of dark matter, if not its entirety, can be concentrated in black holes. So, all right, so let's discuss a little bit of parametric dependence of the abundance, or at least the main qualitative features. So, in cosmology, as many of you know, the main sort of parameter that governs the cosmology is Hubble expansion rate that basically the radius of the universe dot over the radius of the universe, and in the matter radiation radiation dominance equality, it scales as 1 over t, and this is roughly of 1 over 350 seconds times the temperature of the background in units of 10 to the 9 kilo electron volts. Kelvins squared. Of course, if you look under the hood here, it's 1 over m Planck, square root of the number of degrees of freedom times t squared, and that is main thing in cosmology. So 1 over h gives you characteristic time available for any process, and if the process is occurring with a rate much larger than than h, then it means that the system will try to find equilibrium for this process, right? Very well. So WIMPs correspond to the something that is initially in equilibrium. That means that if the temperature is above the mass of, say, dark matter, then chi to Stern model interconversion is fast, and the number of chi's is proportional to the number of other species, as was said before, right? So once the temperature becomes comparable to the masses, of course, the Boltzmann suppression kicks in, and well, I guess I have this plot somewhere here, and then you have of very terrible qualities, however, and then you have so this is the inverse temperature in some units, and then you have the more of the annihilation you have, the sort of the stronger residual suppression of the dark matter you will have. in the end. So if I go back to this slide, and then for example normalize something, let me normalize the rho of chi onto which is energy density, onto something that is will be a mass of the proton times the number density of baryons minus the number density of antibaryons, which is a convenient quantity. Then you would sort of want this to freeze out at the level of 5 or 6, right? And this is what we know exactly that number, right? But anyways, for the sake of this qualitative discussion, you want to freeze out at that level. So you start actually at a much larger level, and then because you start with a number of gammas, which is far more numerous than the baryons, and then there is a very sharp drop in the number densities until the time when the annihilation can no longer catch up with the Hubble, and this is the short period of intense annihilation at T on the order of mass of the dark matter. So, and then we end up with a flat curve later at 5 to the 6. And if you plug in the numbers, this temperature would have to be on the order of sort of 5% of the mass of the dark matter. This is for electroweak scale particles, or thereabout. Gives the right amount of the dark matter. So this is the very sort of non-technical overview of what happens with WIMPs and how they get their abundance. If there are particles that are really weakly interacting, then by the way, large couplings for WIMPs pretty much guarantee that they're in the thermal equilibrium. There is no such thing that we would say, oh, if they're in thermal equilibrium, or what is their initial abundance. The abundance will, by this process, will always be driven to thermal equilibrium if the couplings are not excessively small. This is different for other two examples. So super WIMPs couplings are tiny, and we are sensitive, or they are sensitive to initial conditions. Okay? Meaning that at all times, the rate of the Stern model particles going to the dark matter relative to the Hubble is much smaller than 1. So if that is the case, then of course you are very sensitive to these particles, very sensitive to the initial conditions, and one of the possibilities is that the very early moments of the universe, where say inflation ended and the inflaton decayed to thermal matter, the dark matter was not created in this process. Let's say that the inflaton was somehow decoupled from these particles. Then n chi at the T max sort of 0 is could be a natural starting point. If so, for example, the Stern model processes going in reverse, what we discussed last time, through, for example, A prime, A and A prime going to chi chi. This type of processes generate a thermal leakage of the Stern model into the chi. And if I allow myself to plot it the very same way, the number of the energy density of the skies relative to the mass of the proton times and baryon minus and baryon bar. Well, you can say why do I write it this way? You don't have to. I'm just saying this way I can scale this quantity to to temperatures much above the baryon mass, where the baryons are very abundant in the universe, but their difference is controlled, right? Because it's a conserved quantity. Anyways, so we start from the right. So this is time, by the way, and so this is I should say that this is time. And I just remind again that the time and temperature put here scales as small t time scales as 1 over temperature squared. So this type of behavior of freezing often comes in. A particle comes in with a zero initial abundance at the Big Bang, and then gradually achieves again this level of 5 to 6 through the freezing process, where again the inflection point where you can stop at the temperatures on the order of the mass of the chi, and that is and if you increase temperature time more, the temperature drops further, and all the production, in addition to small couplings, becomes Boltzmann suppressed. So this is the main qualitative features of super WIMPs, and the bosonic condensate dark matter is something not possibly other lecturers will cover. I'm just going to say that if the mass of the say particles small, it's equivalent to think of them as the smooth classical fields, and their occupation numbers are very large. There are sometimes questions that are non-trivial as to whether this is they form Bose-Einstein condensate. Is this a really classical condensate or not? I will shy away from this topic because it's not my main goal. But the main point is that the equations are, of course, governed by the basically a covariant box of say, well, how do we call this field of A in the sort of expanding universe background equals to a mass term, if this is the leading term times A. Now I have to figure out the sign. Sorry. I think it's a minus sign. Well, we gotta get the sign. It has to be chosen such that we have oscillating behavior later on. So they basically this translates to A double dot plus 3H A dot, and this is here is minus sign plus m squared A equals to 0 equation, and one of course recognizes just looking at this equation the equation with viscosity where or friction rather, where H plays the parameter over friction. So if you open the corresponding mechanics books, you will find out that if the friction is large, the oscillations are overdamped, and when it drops below the forcing term M here, the oscillations occur. And of course, from the point of view of the rho of A, we will have the behavior that there is, and then let's say this is the logarithm of the scale factor of the universe. Okay, so if from that point of view, we have we have constant value at the very beginning, and then when temperature now doesn't matter because it's not in the thermal context, but when the Hubble scale becomes comparable to the mass, the oscillations start developing in this equation, and the overall amplitude drops here due to the sort of effective friction, but you can sort of figure that out from the conservation of energy itself, and then there is sort of a -3 slope. But if you draw it in the same plane here as here, well, this is T gamma, then with the same rho of A over MP and B minus and B bar, you will actually discover that yes, it has a very similar behavior. Initially, say the axioms are super numerous, right? But their initial abundance relative to other species is very small, right? They're not scaling at all. The energy density remains frozen. When the field is not oscillating, is as good as the cosmological constant lambda. So they're constantly gaining on this species, and one on the other species. But once the oscillations start, that thing asymptotes to a constant, and you have the very same behavior as in a freezing case. This is a very non-technical kind of review of the main aspects of particle dark matter and how the abundances may have come about, right? And there is absolutely no way a priori to prefer something or one option over the other, right? You can have your sort of theoretical preferences. You would say, oh, it's much more natural to have couplings order 1, but you know, this is a big assumption, maybe, right? Maybe WIMPs are more preferable than the other candidates, but it's mostly driven by, I guess, our ability to detect WIMPs or to search for them rather efficiently. So I wouldn't put my money on any of the scenarios right now. Each of them can be equally valid. All right, so returning to the weakly interacting massive particles. This is very, of course, the idea is lifted from the normal cosmology, where we have a huge number of electrons or positrons above than 1 MeV. then they annihilate, dump their energy into photons as the neutrinos already decoupled, and we have seen the kind of the observational consequences of that, with the energy density in photons being larger than the energy densities in neutrinos, right? So this is developments of the last 15 years in cosmology. We now see rather firmly the presence of the neutrino background through its gravity at the time of the CMB and structure formation. All right, we lift this idea, we translate it to the now massive particles, as was done by this gentleman, and then the sort of mnemonic rule is that the annihilation rate times the velocity averaged over the thermal bath is actually 1 picobarn times c. And if you translate 1 picobarn, which is 10 minus 36 centimeters squared, into some particle physics units, which I'm taking here alpha squared, alpha electromagnetic times lambda squared, where lambda is the energy scale, you get to 140 GeV, which is very nice because it's a weak scale, and then it's a natural scale. And well, I don't know, should avoid the word natural. It's a reasonable scale in nature, let's put it this way, the scale of weak interactions, and that's why we call it weakly interacting massive particles. And
may I ask, Maxim? So I think Lee Weinberg bound that mentioned yesterday. What is Dolgov-Zeldovich?
Right, there was you know, mirroring papers back in the Soviet Union. Back then, the connection between the Western science and Soviet science was let's put it this way, less intimate than it is now, right? So Lee and Weinberg are much credited, but Dolgov and Zeldovich had a review back then with very same mechanisms pointed out independently. That's what I haven't researched myself about the credits and so on, right? Is that the question? Yeah. So
yes, I was just curious.
Yeah, I mean, like Dolgov and Zeldovich were working on neutrinos in the early universe. Okay, back then the neutrino masses were not quite clear, right? You add a neutrino that is heavy, and well, tau neutrino. I mean, everything was light, but it was a natural question. So. What's going to happen, right? So they've looked at this as well. So apparently then there is early 1980s review. Back in the day, it was very famous.
We have a nice comment by Matthias Frenzel, who says that Dolgov and Zeldovich are both mentioned in Weinberg's paper.
Okay, very nice. I wish I knew literature a little better, right? But at least I put their names, right? So that's I to be absolutely frank, I learned about it from Sasha Dolgov, right? He said, "Oh yeah, of course we knew about this." Okay, fine. Of course I knew, right? Very well. So sort of going back to this examples of the dark matter Stern model mediation, yes, we can provide very many simplistic models or more complicated structures based, for example, on supersymmetry and so on. And one of the things we hear much is that 2-to-2 processes are relatively predictive, yeah, so if you have something like the mediation of due to the Higgs boson, then you need to know only that coupling, right? Nothing else. The rest is follows through, and then you put this diagram on the side. You have a scattering, and in some sense, the annihilation. The knowledge about the annihilation size leads to the knowledge about the T channel. If this is an S channel, there is a T channel, and that's very relevant for direct detection. And this is true to a certain extent, but not always true, right? And that's the things that I wanted to discuss next. So for WIMPs, it's very important that maybe it's quite important. Even the small details about the kinematics are very important for the direct detection. The direct detection is in some sense a fragile thing, and that is related to the fact that the WIMPs now are very non-relativistic. They carry 10 to the minus 6 of their mass energy density as an actual kinetic energy density, and therefore anything that you will do to their masses even at a small level may actually affect this. So for example, if you have say let's say you have a scalar, which is scalar 1 plus I scalar 2, and then you can have chi star annihilation due to the dark photon or Z boson or whatnot. That this is the into the Stern model. This is and if I say A prime, that means that I'm kind of referring to my previous lecture, and I borrow all the machinery for the coupling of A prime to the Stern model via kinetic mixing or something very similar, right? So for the temperature, so the mass term, right, that you write down, which is minus m squared chi star chi, is U1 invariant. But if there are terms that break this, right, of something like m, delta m, and then there will be chi minus or plus chi star, that will break this degeneracy, and this delta m can be very small, right? So let's say delta m is, I don't know, 10 minus 3 of the mass. Then for the temperatures on the order of sort of 10% of dark matter mass, when the annihilation happens, this parameter is irrelevant, right? Because it's so small, right? So in other words, S1 can annihilate in this diagram. It's is S1 S2 coupling, right? And then one of them, let's say, is due to this mass term is heavier, right? But it doesn't matter. They're both populated and they can annihilate very freely. But if you drop this diagram into the T channel, say a lighter particle can only go to the heavy particle due to the same sort of A prime Z mediation if its kinetic energy is larger than delta m. So a lighter particle scattering may be compromised, right, by delta M. This often refers as inelastic dark matter, and it's a very simple way of seeing that the kinematics can play nasty tricks to you and to your model, right? Another possibility is also not I don't know. I'm discussing gloomy possibilities for direct detection. Another possibility is that well, the thing about this mechanism is that this is all what you know and all what you need. Annihilation rate, right? How it's organized is not clear. You know, so in particular, if you take one of the models that I discussed last time, you have say dark matter annihilating to two on-shell mediators, which decays into a Stern model. There are two sets of couplings involved. There is, let's say, coupling 1 and the coupling 2 involved, right, for the decay of S to the Stern model. But then the annihilation rate will only scale as the coupling 1 squared, right, and will be independent on coupling 2 as long as this S decays in time, right? And the time is available for it in terms of the microscopic life of S is infinite. So lambda 2 could be whatever, 10 minus 10, right? So it can be a tiny coupling, right? However, if you want to write something like an exchange of the skies, maybe this is this type of diagram, and these are S particles. If you have an exchange of the skies due to S, the coupling of this chi to the Stern model will be proportional to lambda 2. So the scattering cross-section will necessarily scale as lambda 1 squared, lambda 2 squared. So in that sense, scattering cross-section can be indeed super much smaller than the annihilation cross-section. If you tell me that this is an exotic possibility, I will absolutely strongly disagree. This is not. In the Stern model, we see this all over the place. And the most famous example of disparity between the cross-section for, say, creating a particle and cross-section for scattering the particle is the neutrino physics. If we collide protons and the protons, right? So there is an underlying, like, let's say, quark annihilation and so on. That leads to creation of neutrinos. And of course, if this occurs due to the weak interaction, the rate is going to be proportional to the G Fermi squared. But it never occurs that directly, right? You form mesons. So look at this here, right? It's the same idea. First, you form mesons that are then kinematically trapped, and they'll have to decay to neutrinos. So if you just ask the question, what is the cross-section for creating some 100 MeV neutrinos out of the collisions of protons that are a few hundred MeV of kinetic energy or more? And then the answer is, well, it's going to be a strong interaction cross-section, because all what you need to do is to create charged pions. However, if you go back and you ask the question, what is the probability of scattering for the neutrino, then you will find out that, oh, this is a tiny probability, because everything for the scattering will be proportional to the amplitude is proportional to G Fermi. That's why when you do the neutrino physics, the production is not an issue. You have lots, right? But the detector has to be a significant size, otherwise you won't have any detection. And so the very same can be with the dark matter. I'll just, in the interest of time, skip this. Well, one of the things that is important that we often need to know whether the annihilation is P wave or S wave. Why is it important? It is important, well, it's somewhat important for freeze-out calculation, but it's not crucial. It's very important usually for deriving indirect detection bounds or the bounds coming from the late energy injection due to the CMB. And for that, the kinematics is very crucial. And it's often the case that it's easy to predict the dominance of a given wave given the spin and properties of dark matter particles and mediators. So in that regard, here's the problem also for discussion session. Assume that all interactions conserve discrete symmetry, and then prove that if the dark matter is a scalar, then the annihilation of particle and its antiparticle via dark photon gives a P wave annihilation for scalars, and if this chi is a Dirac fermion, it gives an S wave annihilation. Then if the dark matter is light, the S wave annihilation will most likely kill it during the time of the CMB. That is, not to kill it, but it will lead to a disproportional amount of the energy deposition inconsistent with data. Now, also, you can also determine S or P wave character, and remind you this is a total angular momentum, sorry, orbital momentum 0 or 1 of annihilation if it proceeds to a pair of scalar mediators, like I discussed last time. And the answer here is that if it's a scalar pair of scalars going to another pair of scalars, is almost evidently S wave. But if it's two fermions interacting with the parity conserving couplings, then you get the P wave, and that is again for as far as the light dark matter for interests say of light dark matter, meaning sub GeV, P wave annihilation is much preferred. Well, this thing I agree. I mean, this is all correct. However, even if it's an S wave, we can go back to this crucial cases and actually point out that again, a small perturbation to a mass spectrum may actually kill the annihilation at a later day. That is, this delta M would be unimportant for the freeze out, but when you try to mirror the very same picture at the time of the CMB, this such small parameters delta M may prove to be crucial and you know, kill the annihilation rates completely. So even in all this cosmology, bounds have to be I'd say applied with care, and the models would you cannot make blanket statements, and the models would have to be examined probably very tightly to understand whether they survive or not the CMB bounds. All right, so don't know why my print cut these things. Okay. So if I decipher what's written here, it's written 2 additional blind spots for direct detection. And so, and I'm realizing that I'm going very slowly and probably running out of time soon. So I wanted to actually discuss a little bit the stuff that was voiced last time in the question session as to what happens with if we drop the mass of dark matter to MeV scale, and why the detection is possible even with today's instruments, although naively, mass of an MeV means that the kinetic energy is less than an EV, and probably only now there are appearing instruments that then can be that low. And another sort of favorite topic of mine, and this probably refers only to subdominant components of dark matter, is that, so imagine that you have a particle that is really strongly interacting, let's say 10 to the minus 24 centimeters squared, right? So, well, and the current bounds are 10 minus 46 centimeters squared. You would say, oh, well, I should be able to see this particle, even if its abundance is, like 20 orders of magnitude below the abundance of dark matter. But that's a premature answer, because such particles would thermalize very quickly before reaching the places where you have much sensitivity in low radiation backgrounds, such as underground labs. So in that case, the kinetic energy of the particles may very quickly drop to thermal energies, and then you need really, really low thresholds to start seeing that, right? So,
Maxim, we have a question for Einar.
Yeah, please, yes.
Yeah, I was just wondering if these strongly interacting dark matter models wouldn't be ruled out by other experiments, such as beam dumps.
There will be constraints, yes, but if they say the mass of this dark matter is 10 GeV, then no beam dump will produce it.
Yeah, okay, I see. Yeah, right.
Yeah. So, the current, like beam dumps, okay, if you have an SPS beam of 400 GeV, then the center of mass energy equivalent nucleon is, I forgot, 20 or 30 GeV, so you just can't produce it. Right?
Well, but that's still, I mean, if there existed a particle with a mass of, say, 50 GeV that was fairly strongly interacting with the standard model, I mean, we would see it at the LHC or something, right? I mean, I find it hard to believe that it wouldn't show up in some of the high energy experiments.
Well, you can formulate any particular model and try to see it, right? I mean, like, I can present you concrete models where the cross sections are sizable, but particles are not really all that discoverable. Again, this is like if you take a chi that is say 10 GeV in mass, and you have a mediator with sort of that is dark photon mediator, which, let's say, I don't know, 100 MeV and kind of 10 minus 3 mixing angle. This very fairly sizable cross section, right? But when you talk about the LHC, this is not going to be, because here there is a light scale built into the scattering. So the cross section for scattering will come out to be quite large, but the cross section for pair production of this guy will be very small.
Right, I see. Okay, yes, Yes.
So what I'm trying to say, you're right. There may be some classes of these models that are, would give lots of missing energy plus a jet or something that is inconsistent with LHC, but not necessarily. So I happen to work on this in the last few months, so I am absolutely certain in what I'm saying. So there are models that are actually completely escaping any constraints, but I would emphasize that this refers to mostly subdominant components of dark matter.
Right. Okay. Thanks.
All right. So I guess when we talk about light WIMPs and what is the main limitation? What's the problem? So as we all know, right, the dark matter distribution or flux on the Earth. Let's go back to the weakly interacting dark matter, or for which the Earth is transparent. Let's say then. The distribution is such that it's sort of quasi-Maxwellian with a cutoff, and there isn't any Boltzmann tail because the tail flew away. Okay, so and then you can ask the question: are there any fast dark matter particles? And this is what we kind of looked at some years ago, now maybe 4 years ago, when I was looking at this plot. There would be a xenon 10, xenon 100 constraints, and then no limits, right? I mean, for the light dark matter, and this was very puzzling, right? And it's clear that it cannot be the case. Because if the cross sections are large, if the cross section is 10 minus 36 on centimeters squared on electrons, and you send a particle through the sun, it sort of scatters with order 1 probability. The probability approaches order 1 for this type of cross section, right? So it means that there can be an upscattering where the particles will inherit the energy of electrons inside the sun, and then sort of that would on this distribution would create a small but energetic tail that will stick above the experimental threshold. That is very simple idea. So here's the results of our original simulation with some estimates. This, of course, I mean, we are close to the sun, but not that close. If you look at the sun, it subtends only sort of 10⁻⁵ of the or thereabout 10⁻⁶ of the solid angle in the sky, and that's only that place will be shining with energetic dark matter. So the best analogy of this is actually Sunyaev-Zeldovich effect, right? So we have the CMB of a fixed frequency, but when it passes through a point in the universe where there's a lot of energetic electrons, the CMB can be moved from one frequency band to a higher frequency band, showing a very specific spectral distortion. Okay, but photons are fortunately very easy to detect, so you observe this effect very firmly indeed, and this is just a normal physics. So translating this to the dark matter gives us a new tool of studying this dark matter, here's the constraints from our original kind of paper, and they didn't come out very well here. So there's new limits set by sort of reappraisal of this mechanism by a paper that's about to appear and by a recent paper by MCAN. So the point is that I guess the point is that the kind of the 10⁻36 benchmark is almost universally kind of covered by various experiments, if you like. But the 10⁻36 is a fairly small cross section. All right. And of course, 10⁻36 is a picobarn, I forgot to say. But then still there is a large part of the parameter space, for example, for a simple minded freeze-out model that is still not covered and will be covered perhaps by the next generation of this sensei experiment, or already being covered by but we don't know yet. So then we kind of double down on this idea with Brinkman by saying, oh, we can say play the same trick with cosmic rays. So if there is particles that are you know, interacting with nucleons somewhat strongly, and then not really doing much for the direct detection, you can have rare collisions with cosmic rays that carry a lot of energy, and that can shift these particles into really like fast gear, right? And then they can go and scatter not only in sort of direct detection experiments, but also with the neutrino experiments here, right? Because they can carry enough energy to be detectable by neutrino experiments that in general still have lower counts than dark matter experiments. So if you can use, for example, super K scattering, then you should be doing that, right? Yeah. Very well, and that was further augmented to show that there are no gaps here, and then in this sort of framework, everything up until sort of 10⁻31 centimeters squared is more or less covered. So this is a nice exercise, I would say. All right, and then the last idea with respect to WIMPs I wanted to mention is that there is another blind spot about this thermalized dark matter component. And what's interesting about it is that the dark matter, even if it's at rest, completely at rest, is a reservoir of energy, of a momentum, a large momentum recoil in principle, if your state is excited. So Akim discussed with you nuclear excited states, and he discussed with you states that are relatively fast decaying, but the nuclei are very peculiar objects compared to atoms. There are states that can live forever and ever, and there is, for example, a very famous case of an odd nucleus, 180 M tantalum. This is M stands for an isomer. This is things that is an excited nuclear state, lives billions of years. There is not a detected decay to that nucleus, and it's separated from the ground state by something like 100 well, it's very well known now it's separated, but I forgot, 70 or 100 keV energy splitting. And well, this is interesting because you can sort of have this M variety of the nucleus, 1 ATM, could go to the ground state of the nucleus due to the scattering on chi that is completely at rest. You don't need its kinetic energy. All what you need is to a massive body to recoil against. And this is going to happen because the momentum transfer in this game will be proportional to the 2 mu times, I guess you've seen a lot of kinematic formulas in the last 2 days, delta E, and that is going to be much, much larger than the Q of gamma that you may emit from going from 180 M to the ground state. And that is the smallness of the Q of gamma relative to the radius of the nucleus, that is what leads to the enormous suppression of this rate, because these 2 things, I neglected to say, ground state and excited state have an enormous disparity in angular momentum. So the recoil on the thermalized fraction of dark matter can circumvent the selection rules with respect to the angular momentum, and some experimental colleagues even have done some searches, repurposing older studies of 180 M tantalum for particle physics, like, what is this weird thing? But for nuclear physicists, this is a very, very important question, what this thing is, because it's very surprising that you got 0.01% fraction of all thallium into that odd nucleus. It is a question how it got formed. Anyways, I don't have much time left, so do I have like a few minutes?
Yes, sure, go ahead. A few minutes is okay.
So I would maybe just finish up with freezing dark matter, and I stop with the WIMPs at this point, and with the freezing dark matter, returning to this plots where you have nothing initially, and then you have got right to the spot where it's dark matter. This is the idea. If you had initially too much, well, then tough luck, your model is dead, right? Because the couplings are small, then everything, all the kind of rates are small. There is no way of depopulating this. But then the tiny couplings means that the lifetime can be for a particle can be much larger than the lifetime of the universe, and then the stability of particles is not an issue anymore, right? So both it may be that it's not an issue, right? So if the mass of chi is generally small and the coupling is small, so is the decay rate, so that the longevity much larger than the lifetime of the universe can be very much satisfied, and this opens up a possibility of unstable, metastable particles as dark matter. So both sort of Stair model going to a pair of super WIMPs or freezing dark matter or as single particles, it suddenly becomes on the table. For WIMPs, we usually don't do that, or you really have to decouple their decays from the production mechanism, right? And the examples include sterile neutrinos, dark photons, and gravitinos, right? So we don't have time to go over much of it. So for dark photons, perhaps gravitinos is an interesting example where you first can go from the Stern model you can combine kind of the WIMP ideas and the decay ideas. So you first go from next to light supersymmetric particle into the standard model freeze out, followed by chi to gravitino decay. So this is an option that is known to particle physicists since I don't know, 70s or 80s. Very well, but then in the last couple of decades, these two other options are being discussed quite thoroughly, and in particular, there is a nice paper here for the basically new to n estimate, where you would estimate the abundance of new HNL heavy neutron lepton neutrinos relative to the neutrinos as effective mixing angle squared. I'm just have no time to dwell on this, times the so basically gamma of the neutrino scattering, of regular neutrino scattering, times delta t, or the integrated over time, which means you have to do dt over t Hubble rate, and this thing receives a matter suppression. So the bottom line that this production mechanism kind of peaks at the temperatures comparable to some MEVs if the mass of the sterile neutrinos in KV. Sorry, I'm doing a bad job here because I don't have time. So if you go through this, and then there is a nice review by Kev, where you can see that this simple minimal Doddelson-Woodrow mechanism is actually being under pressure from indirect detection, when particles are unstable in some fraction of times, and decays to gamma and the neutrino, and you can look for this gamma and not finding it sets very, very strong bounds. There is also famously an excess here that people have speculated that might be related to a freezing dark matter. And then finally, that there is also calculations for freezing calculations for dark photons, where if you take 100 keV mass dark photon, it turns out that you need a coupling of 10 to the minus 11. So you would think that this should be safe from anything observational, but actually no. That the combination of gamma backgrounds constraints, stellar energy losses, and direct searches using xenon, where you take a xenon atom and you add a dark photon that is, if it's in 100 keV range, and with this coupling is sort of quasi-stable, lives much longer than a lifetime of the universe, and you get xenon atom plus an electron. So this is the process that is very sensitive all the way down to 10 minus 13 kinetic mixing, while the freezing calculation requires 10 to the minus 11. So this is an interesting case where you'd say, oh, such a small coupling it must be absolutely safe, but no. Even such couplings can be constrained by very sensitive experiments. I don't have time, so for the coherent field oscillations in more detail, so see Andreas Ringwald lectures. This is a very nice concept, but the problem, unless it's an axion, the standard model axion, QCD axion that is introduced to cure the standard model yields of strong CP problem. Unless it's not, there is no prediction of what the coupling is, right? So at least for the WIMPs and super WIMPs, the coupling to the standard model was required. Here it's not. All right, sorry, I stayed over time, and I'm just going to conclude with dark sectors provide a broad perspective on dark matter and perhaps associated particles. Several mechanisms for generating abundance exist. Blind spot in direct detection of WIMPs gradually get covered, and we just talked about this reflected from various energetic particles WIMPs, which works well if they're light, all options in my mind remain viable for generating these abundances, and all these classes of dark matter remain viable. However, some become disfavored, and in the absence of the discovery of non-gravitational interaction of dark matter, this constitutes progress. So Friesen dark photon model is, for example, is ruled out, and Doddelson-Woodrow style Friesen heavy neutral lepton dark matter is also ruled out, etc. I'll stop here. Thank you.